This is Math 30-1, where we are again in Chapter 5, looking at exponential and logarithmic functions and equations. We have reached our final lesson, which is looking at applications that involve exponential and logarithm. So we've looked at a few of these questions earlier, a few application questions. So just a reminder here to begin with under these notes. For this course, you'll be given a formula for application questions unless the question fits into this kind of general form. So let's first of all look down here, this growth and decay formula. This is the formula that we're given on the formula sheet here, where y is equal to a times b to the exponent t over p. So that's the formula given on our formula sheet. And then up above is what I have kind of rewritten as a summary. The y value is going to be the final amount. The a is an initial amount. The b is a growth or decay factor, depending on whether things are getting bigger or smaller. And then the exponent, we have the t, which is the total time, and then the p, which is the time for one period of growth or decay to happen. Now, compound interest questions, we looked at some of those earlier in this chapter. They're considered to be variations of this formula, and so the compound interest formula will not be given. So we're expected to know that. Well, now as you look down on this page, you will see a couple of warm-up questions, similar to questions we've done earlier in the chapter. So why don't you pause the video at this point to work through these two questions. Pause the video now. Well, you'll remember that y is our future amount. That's what we're asked to find for this question. When we're asked for a maturity value, that's going to be the value at the end of this term. A is the initial amount, so that will be our $3,500. B is our growth rate. In this case, we have 4.5% per year, but it's compounded quarterly. So our growth rate will keep the 100%, and we're going to add that 4.5%, but we need it as a percent interest per quarter, so we want to divide that by 4. So this will be our b value in the equation. We're interested at the end of a 5-year term, and if we go with the formula as we were given above, this t would be a time in years, and so that's going to be 5 years. The p is how frequently per year our money is compounded, and it's compounded in every 1/4 years. So again, these two need to have the same units. So when we come to writing our equation, we will have y is equal to our initial amount times our growth rate to the exponent. Now, in my exponent, let me just combine these together. That would be a t over p, so that would be a 5 over 1/4. So how many times does a quarter go into 5? Well, that will give me a 20. So rather than writing it in the exponent there as the fraction, I'm just going to rewrite it as a 20 here right away. And now we just have numbers that we can plug into the calculator to evaluate and determine what our y value is. And what we will find is that the maturity value of the investment is about $4,377.63. In question number 2, now we have a vehicle depreciating at a rate of 19.2% per year, compounded monthly. Now this may look like an extreme rate of depreciation, but it's actually not far off for new vehicles. So particularly in the first 4 or 5 years, a vehicle may depreciate at a rate that's close to this. So again, let's list out the information that we have from the question. We have the depreciation rate of this much per year, and so I'm going to jump right down to my b value. I'm starting with 100%, but it's depreciating, so now I'm going to subtract. and that's 19.2% in decimal form, but it's compounded monthly. So I'm going to divide this by 12 to get a monthly depreciation rate. We want to know in how many months it will take for the value of the vehicle to reach half of its original amount. So since I want to know the number of months, I'm going to say this time is going to be some mystery value in months, which means my period will be monthly. Well, it's compounded once per month, so every 1 month is the compounding period. Notice in that previous question, it was every quarter year that our investment was compounded. But now it's compounded once a month, so since I picked months for t, because that's how I want to find my answer, I used months for p as well. And then that's pretty much all we're told, except that our vehicle will be worth half its original purchase price. So we can pick any numbers that we like here for A for my initial value, as long as my Y will be half as big. So I could say, well, let's say my A value is 1, imagining that means 100%, which means my future amount will be 0.5 or 50% of that initial amount. It wouldn't matter what numbers I picked here. I could pick 1,000 and then 500, as long as Y is half as big as my A value. So here's what my equation will look like. And we want to solve for what the t is in the exponent. Now, previously when we did these questions, we solved by graphing, but now we know how to solve this algebraically. When I simplify my base, this is what I get. And now, since I have a power equal to a number, I could just rewrite this in logarithmic form. So my exponent is equal to my logarithm. The base is this 0.984, and it's operating on this 0.5. And we can plug that into the calculator as it is, if your calculator will work in different bases. Or if you need to change this to base 10, you could enter it as the log of 0.5 or log of a half divided by the log of 0.984 to evaluate our answer. And for this question, what we will end up with is that the vehicle will depreciate to half its original amount in about 43 months, which is 3 years and 7 months, which is a little bit sad if you're buying a new vehicle. Well, let's continue on to look at some more examples. Here we have a particular population of bacteria tripling every 7 hours. So let me enter that much information so far. I have my growth rate. It is tripling. How frequently? Every 7 hours. So that rate of tripling happens once every 7 hours. So I'm going to stick the units here again, because if my units for P are hours, my units for T also have to be hours. How long will it take? Well, that's what I'm going to be solving for, the time here. For the sample of 20 bacteria, so that's my initial amount, 20 bacteria to grow to 20,000. And again, as we've looked at previously, these two terms have the same units, so these are bacteria. These two also have the same units, and in this case, it's going to be a time in hours. With this much information, we can write our equation. And as you look at this equation, you'll see that the equations that we get for these application questions are often simpler than the equations that we solved in our previous lesson, which is kind of nice. We'll start by dividing that 20 out to get 1,000 equal to 3 to the exponent p over 7. Rewriting this in logarithmic form, my exponent at t over 7 is equal to log base 3 of 1,000. And then as I isolate my t, I'll get 7 times that logarithm base 3 of 1,000 and evaluate that to get our answer, which we discover is about 44 hours, 44.0 if we go to the nearest tenth of an hour. Our next example is looking at half-life. So the half-life of a substance is the length of time it takes for the substance to decay to half of its original amount. So the half-life would be the p-value in our typical exponential equation. So in this question, we have some plutonium-210. It's radioactive with a half-life of 20 weeks. If we're starting with a sample of 80 grams, we want to know how much will remain, first of all, after 20 weeks, and then 40, 60, and then we'll sketch a graph and have a look at what's happening here. Well, we know here that our half-life is 20 weeks. So if we're starting with 80 grams, then after 20 weeks, we'll have half that amount left over. We'll have 40 grams. Well, if 20 more weeks pass, then we can say we'll take that 40 grams and find half of that, which will leave us with 20 grams. 20 more weeks, we'll take half of that 20 grams, and we get 10 grams left. So if we were to sketch a graph, here's what these points will look like. And I connected the dots as well. So here, we're starting with the 80 grams here, which will be right along the y-axis at a time of 0. 20 weeks later, we have half as much. 20 weeks after that, half as much as we had at 20 weeks. And then 20 more weeks, half and half. And it would continue like that, halving every time. So we'd say that's the half-life for plutonium-210. Now, question number 6 is also dealing with a half-life, but a different element. After T hours, we're told that only 3 1/8% of the radioactive element remains. So we could say, well, let's imagine that we are beginning with 100%. So my initial amount is 100%, and I could write it as a 1 or as the 100. I chose to do it as 100 this time. It's not going to matter. But as long as I make sure I'm the same as I write this future amount, where we're told that 3 1/8%. So that'll be 3.125 is 3 1/8% left over. So there's my future amount and my initial amount. Additionally, in this question, we're told that we have a half-life of 3 hours. So my B value will be a half, and my P value will be 3 hours. And we want to determine how much time has passed. So there are values. We can substitute them into the equation to solve. Why don't you pause the video at this point, finish off the question, and then restart the video to compare your answer with mine. Well, here you can see my process, and when I substitute it into the calculator, I discover that the time that will have passed is 15 hours in order for that element to decay to 3 1/8% of the initial amount. On the next page, here's a question for you to try. So pause the video again, work through this question, and then restart the video. So these are the values that I got for each of the parameters, and hopefully yours look the same as mine. And then when we write our equation, we'll come up with this. And then we solve. Now we're solving for the p-value, which was in the denominator. So I need to do some more manipulating this time. I get this exact value expression, and then in terms of an answer, I get about 281.5 days in order for uh, us to figure out this half-life. Let's look at a couple different types of questions. First of all, we'll look at earthquakes. An earthquake happens when potential energy is built up, when tectonic plates create pressure against each other and the friction doesn't allow them to move, but then once they move, that potential energy is transformed to kinetic energy, and that energy released causes movement to the ground. The intensity of an earthquake describes the ground motion, and it's measured on a seismograph or seismometer. The magnitude of an earthquake is a way that we have of describing the size of an earthquake. So it describes the energy that's released, and we would say a magnitude 1 describes an earthquake that's, or I should say an increase of a magnitude of 1 describes an earthquake that's 10 times more intense. So what we'll find with a lot of these applications is we're looking at comparisons, as in how many times more intense is one earthquake than another earthquake. So we'll look at that kind of situation. Because a magnitude 1 earthquake is just arbitrarily chosen, which means it's random. Somebody decided, oh, this is how we're going to measure earthquakes, and we'll call this a 1. Why? Because we need some starting point. So the ground motion that causes 10 times more would be a magnitude 2 earthquake. And so we can see that there's exponential growth in terms of the intensity, and so we can have a logarithmic relationship when we look at the magnitude. So here are two fairly typical types of equations that we're given. So this first one is looking at intensity. This I sub 0 is the reference intensity, so for magnitude 1, and then I would be the intensity for some mystery earthquake that has a magnitude of m. And that's often the Richter number is what we'd refer to, the Richter scale that was created by, I can't remember his first name, but Richter was his last name, apparently. So let's look at this equation, or this example. So suppose we're given this equation at the bottom, the I over I sub 0 equals 10 to the magnitude m. The two most deadly earthquakes in the first 4 months of 2016 were in Taiwan and Ecuador. The Taiwan earthquake had a magnitude of 6.4, and Ecuador had a magnitude of 7.8. We want to know how many times as intense was Ecuador compared to Taiwan. Well, let's begin this question by doing some rearranging of this equation. In this equation, I'm going to take this I sub 0 and I'm going to multiply it to the other side. And so I would get the intensity of an earthquake will be that reference intensity times 10 to the exponent m. Now, the reason I want to do this is because I know the intensity. Well, I want to know how many times as intense it was. So I want to take the intensity of the earthquake, which was the larger one. Let's see. Ecuador was a larger one, so I want to find that intensity, and I want to compare it to the intensity of the earthquake in Taiwan. So I can find this ratio. Well, I can do a substitution where I know I have I sub 0 times 10 to the exponent. Here, this had a magnitude of 7.8 in Ecuador. And then in Taiwan, we had a magnitude of 6.4. So as I do this comparison, I can see that these two reference intensities cancel out. So it doesn't even matter what that number is. I can just evaluate this quotient here. And since I'm dividing powers base 10, I can just subtract the exponents, 7.8 minus 6.4, which will give me 10 to the exponent 1.4. And then I just evaluate that on my calculator to discover that the earthquake in Ecuador was about 25 times as intense as the Taiwan earthquake. So even though the change in the magnitude number was only 1.4, that's telling us about 25 times as much energy was released. So 25 times as intense. So that's one type of application. Another application question is looking at the pH of a substance, which would be the power of hydrogen, which looks at the acidity or alkalinity of some chemical substance. Many of you are familiar with this from chemistry, and so you may have ways of answering questions related to this that don't necessarily look at the kind of formulas that we will look at exactly, but it is an application of exponential and logarithmic equations. So an acid is a substance that donates hydrogen ions, a base, a substance that accepts hydrogen ions. And the hydrogen ion is represented by this H with an exponent that looks like of a plus. The acidity, alkalinity are measured on a logarithmic scale, which is called the power of hydrogen. So here, if we look at pure water, and pure water would have power of hydrogen, a pH value of 7. So we'd say that's pretty neutral, and we could say the hydrogen ion concentration is 1. Milk would be 10 times as much concentration, and the pH number decreases by 1. So as pH decreases, our substance becomes more acidic. Here our pH of 7, again we're looking at pure water. If I look at seawater, well, it's 1/10 as many hydrogen ions, so the concentration is less, but we increase the pH number in our description. So that's how they work. Again, our equations are going to look fairly similar. So you'll see these two equations that I put here on the left. Again, we would say that our I sub 0 is going to be the hydrogen ion concentration of pure water. So we're looking at that as being our reference point. The I would be the hydrogen ion concentration of whatever substance we're looking at, and A would be the pH value. So let's look at the next question. If the pH level of rainwater changes from 6.9 to 6.3 in the period of a year, so the pH value decreased, and again, here as we decrease the pH value, we'd say it's becoming more acidic. So the rain has become more acidic in the period of a year. Oh, that's this question. Has it increased in acidity or in alkalinity? Well, we just observed since it's decreasing, the water has become more acidic. Imagine this is our equation that we're looking at as we come up with our equation to solve this problem. Well, here's the initial situation. We have a pH number of 6.9, and we don't know what our hydrogen ion concentration is. But we could rewrite this in exponential form. So my base again is 10, common logarithm when there's no base given. So I have 10 to the exponent 6.9 is equal to this hydrogen ion concentration. Similarly, I can look at the end of the year, my pH number has changed. Again, as I rewrite this in exponential form, I get 10 to the 6.3 is equal to I2. In this question, again, we're interested in how many times as much, in other words, how many times as acidic is the final compared to the initial. Now, this is a bit of an odd one because even though my final has this smaller pH number, I'm going to set up my equation so I put the larger one on top because it's increasing in acidity, so I already know the direction it's going. I just want to know by how much. So I'm going to look at that I1 compared to I2 in this order. So 10 to the 6.9 over 10 to the 6.3, which would give me 10 to the exponent 6.9 minus 6.3, or 10 to the exponent 0.6. And 10 to the 0.6 is about 4. So we'd say the rainwater has become about 4 times more acidic than it was at the beginning of the year. So that small change in pH value is actually fairly significant if we think about the acidity being 4 times as much. Next type of example that also uses the logarithmic scale, and that would be the loudness of sound. Our ears are super sensitive. So the faintest sound that a typical human ear can hear has an intensity of 1 times 10 to the negative 12 watts per square meter. So let's just pause for a moment to think about that. So watt, that's a measure of power, so it would be the sound power, and square meters would be area. So this would be the intensity of the sound. So we could talk about sound energy, and energy over time is power. And then we'd still have the area in the denominator. So if you imagined 1 meter by 1 meter square, and it having an energy of 10 to the negative 12 watts. If you think of light bulbs and the typical incandescent light bulb, that would be maybe 40 or 60 or 100 watts, this is infinitesimally small. So a sound with this intensity will displace particles in the air by a mere 1/1000th of a centimeter. So hardly any movement of the air at all. Sound energy is pretty weak energy, but our ears, being super sensitive, can pick this up. We would say that that would be the threshold of hearing. So that will be our reference intensity for sound. And since the range of intensities that a human ear can detect is so large, the scale that's used is going to be a logarithmic scale with a base of 10. And we call this the decibel scale. So deci may give you a hint that it's not like a meter, but like a decimeter. Okay, so it actually, there would be a bell, which would be a unit for sound, but we use decibels instead. So the threshold of hearing is assigned a sound level of 0 decibels, with an intensity represented by I sub 0 again. And so here we have some examples of some different types of sounds, their intensities, and then what the intensity level would be. And probably this decibel value is what you're more familiar with. So something like 110 decibels, that's pretty loud. That would be like the front row of a rock concert. So your ears can't handle that level of sound for very long. So kind of if you were to look up online to see kind of what your ears can safely handle, what it'll say is kind of once you're above 90 decibels, you should limit the amount of time your ears are exposed to that before they're going to experience damage. So your ears can handle a really loud sound as long as it's not for too long. Well, again, our equation looks similar to the previous equations with a slight variation. So you'll see here that we have this denominator of 10 in the exponent, and we have this 10 that's out in front of our logarithm. So these two are just rearrangements of the same equation, but that 10 that shows up in the denominator here and in front there is because we're dealing with decibels and not just bells. Okay, so once again, our I sub 0, as we mentioned earlier, is going to be the intensity of sound at the threshold of hearing, that's the TOH, and we saw that in the table up here, so how many times it is compared to the TOH, threshold of sound. I would be some intensity for whatever sound we're thinking of, so here, threshold of pain is like 130 decibels. And then L would be the loudness, so that would be our decibel measurement for the sound. So in question number 10, a baby's cry can reach a loudness of 110 decibels. Given that the loudness of a shotgun is 1.5 million times as intense, what is the decibel reading of the shotgun? Suppose we're given this as our starting equation. So what do we know? We know the loudness for the baby is going to be 110 decibels. The loudness for the shotgun, that we don't know. But we do know the comparison of the two intensities is 1.5 million. So this is the information that we're given in the question and what we want to find the loudness of that shotgun. So we look over here at this equation and we want to be able to do a comparison of intensities. We want to rewrite this logarithmic equation into exponential form. Now we have the exponential form above on this page, but pretend we don't. Pretend we actually have to go through the process to figure it out on our own. So we'll start by dividing this 10 out from in front of the logarithm, because we need the logarithm isolated before we can switch this into exponential form. So maybe I'll just do it like this. And I'll bring it all the way over here. Okay. So now as I switch to exponential form, my base from here is 10. So that's why my base in my exponential expression is 10. The logarithm is the exponent. So there's my exponent of L over 10, and that's equal to this ratio of intensities. And so if I rearrange it, I get that the sound intensity will be the threshold of hearing intensity times 10 to the exponent loudness, so my decibel reading over 10. And we want to now set up an equation where we have this ratio of these two sound intensities. So let's start this up on the right here. So we'll look at the intensity of the sound for the shotgun. And that will be I sub 0 times 10 to the exponent loudness over 10. Now I'm just going to move that equal sign because I may as well write this as a ratio right away. Where I can say the shotgun over the intensity of the baby sound. Here I'll have my reference intensity and then 10 to the exponent 110 over 10. Because again, we have that decibel rating of 110 decibels for the loudness for the baby's cry. I know that this ratio, IS over IB, is going to be 1.5 million. So there's my 1.5 million. Here on the right-hand side, these reference intensities cancel out. And I have these powers of 10 that are being divided. So right away, I'm just going to jump and I'm going to subtract the exponents. So I have an L over 10 minus 110 over 10. Now I could have reduced this, but because I already have a common denominator, I kind of like that. So I'm going to think of that all as one expression in a moment. Let's change this into logarithmic form again. So my exponent, which is L minus 110 over that common denominator of 10, so I've simplified that exponent. That's going to equal a log base 10 of the 1.5 million. And I need to solve this to figure out what the L value will be. So the loudness for the shotgun. So I didn't put this subscript of S here with the L just because my L's are small and my writing is a little messy. But let's just keep going here. So I have L minus 110. I can multiply the 10 up to the logarithm. And then I'll add that 110 over to the other side of the equation so that I'll get the loudness of my shotgun sound will equal 10 times the log base 10 of 1.5 million plus that 110 decibels. Fix that, 110 decibels. So what I'm getting in this calculation is how much the loudness increased by, and then I'll add that to the 110. When we evaluate this with our calculators, we will find that the loudness of the shotgun is about 172 decibels. which is extremely loud. You don't want to have your ear very close to that, especially as you look back up at this table where we have the threshold of pain is at about 130 decibels, instant perforation of the eardrum at 160 decibels. You want to have some distance between your ear and the shotgun, or you want to have some ear protection on. And there we go. That finishes this chapter. And there's some questions for you to practice in your workbook. Here's a question to practice from the workbook, a check your understanding question, and then these others to practice. And I've listed out here a few that you should just not even bother looking at. All right, there you go.